everybody. I hope everyone's having a wonderful day. So last day, we had introduced the concept of a tree. Now, you may have seen trees before. I laid out some tree terminology. We described trees as this abstract model for laying out a hierarchical system. So things like organization of a company or a file system. They naturally model trees. There's all sorts of interesting things out there that you can use a tree to model them. Strangely, some weird ones you may never ever thought of. But we're not really here to talk about that at the moment. What we're going to talk about here, at first, before we get into some nitty-gritty, is talk about the tree ADT. So it's worth noting that for simplicity, I'm going to refer to a node in the tree just as a node. And sometimes I might refer to it as a position whenever convenient. Maybe that might happen a little bit later. So there's going to be some other methods or functions that you may define for a tree, depending on what the application is. Sometimes you work with some algorithm that's on some tree. It might have some other operations beyond the ADT. It's pretty common. Now, I want you to assume that the nodes contain elements. I'll go into more detail of how you might implement a tree. So here are some standard methods. So size, get the number of elements in the tree, is empty. We're familiar with most of these. Remember, an iterator, it returns an iterator object, and that will allow me to go through each element in a collection. Remember, we talked about these the other day when I was talking about dictionaries. Then lastly, we have ones for accessing information and those for querying information in the tree. So some of these you might necessarily want to avoid doing, at least from a practical standpoint. Sometimes you don't want to expose what the root is. But these are some other ones you might implement. So for example, the root, returns you the root directly. If not, return null. This will give me a node, it gives me its parent, null if it is the root. This returns me an iterable collection containing the children, so it might give me a list or an iterator that gives me all of those elements, one after the other. One detail I should point out is that this can be done usually efficiently with an iterator. However, if you have a list that's able to just traverse through one after the other in constant time, that's usually what you want. You'll find in our algorithms we talk about with trees, we'll just assume that you can just access one after the other very efficiently like this. Then numchild, this is another one we're going to use a little bit later, possibly. This returns the number of children of a node P. And then these query ones, if you want to know if a node's internal or external, these are Boolean methods that will return back true or false. And if you want to know if the root is P, this will return true if it's the root. This sometimes pops up in some tree algorithms when you're building up or reconstructing or recomputing a value from going from a leaf to the root. We'll see that later on in this course, actually. So you might naturally ask, well, people, then, how might I implement such a tree? Now, you may have seen special kinds of trees in the past, but maybe not general trees in the past. So I'm going to lay out one way you can implement a tree. I'm not going to focus so much on some of these here. Instead, I'm going to focus on what the structure would look like, because a lot of the methods I've laid out are particularly easy to implement if you are sufficiently competent and patient. Because a lot of these things you may have seen the algorithms for, but I'll be showing you a plethora of concepts that you can play around with trees to do such things anyways. One thing I didn't list up here that sometimes comes up is computing the height of a tree. We'll see how to do that actually if we have time today. So I'm going to draw a very elaborate picture. Be warned, it is quite elaborate in quotation marks. So here we go. So we're going to have what is called a linked tree representation. A linked tree representation. Kind of like when we talk about linked list or a linked structure. We're going to be using that type of idea. So imagine I give you a tree that looks like this. C, A, F, D. By the way, what are the children of C? A, F, and D. What's the parent of F? It's C, right? and B, and B. By the way, what's the height of this tree? It's 2, right? You count up the maximum number of ancestors, the maximum depth. Another easy way you can also do it if you don't like counting the ancestors, you just count up the edges from the furthest leaf to the root. That's oftentimes how people talk about the height. Okay, so get ready for this. Okay, so I'm going to have a node that's going to have three attributes to it. It's going to have data, it's going to have some data. It's going to have a parent reference, and it's going to have children. It's all in the family, you see. So I'm going to have a root that's going to refer to the node that contains really the information of the root node. So its data will be referred to as C. It has no parent because it's the root. And it has children. So its children are, you can think of this as a list of nodes. Now, to be careful here, you have to follow the arrow very carefully. I recommend looking at my picture in the notes if you're getting a little lost by this. So I have a reference for the children. This is a list. And now this is going to consist of references to other nodes that are my children in the tree. So I have 3 children, right? 1, 2, 3, right here. So I have 3 fields, 3 fields, and 3 fields. So this is going to be A here. Remember, A is right there. There's no geometric meaning for if it being on the left or the right, technically from a graph theoretic standpoint, but we're imposing an ordering sometimes when we implicitly draw it like this. But don't worry too much about it. It's just a picture. So the parent of A is C. So I have my parent reference points up to the node that is C. And it has no children, right? But remember, this is still a child of the root. So I have a reference in my list to a node, which is A. Same thing here. I have a reference here, that's F. Its parent is the root. And then I have children. So the children, I have a list with 2 elements in it. Each one of those is a reference to 2 children. Remember, I have B and E down there. And then I have my next reference here. This one, of course, it points at F. And then lastly, we have D. D's parent is the root. And it has no children. However, remember, this requires a reference because it's a child of C to that node. We're almost done the picture. Okay, now F has 2 children. Now, fortunately, both of them are leaves, so I know they're children. There are no children. So these are B and E. Then its parent is F. So there's F right there. F right there. And remember, B and E are the children of F. So they must be in the list here of children. And there we go. I think we got everything. There's the linked tree representation. So we have nodes. Remember, each has a data field, a parent, and it has a list of children. So this is usually implemented with an iterator, possibly. Either way, some way of traversing through all those elements. It might be internally stored as a list. We'll say that tends to be pretty common. Okay. So I want to talk a bit more about properties of trees. So this is how you could implement a tree. So this is a very general structure. You may have seen trees that have only 2 children or maybe 1 child. This one is general for how many number of children you would like. So I want to talk about trees more generally. So this is going to be a fundamental tree property that I promise you is going to save your butt many, many times if you're proving things on trees. So I'm going to let M be the number of edges and N be the number of nodes. So M and N. M is going to be the number of edges, N is the number of nodes. This is a very important theorem involving trees. It's a very simple theorem to prove. I want to give you a relationship between the number of edges and the number of nodes. So M is equal to N minus 1. So the number of edges is always going to be 1 less than the number of nodes. So I'm going to first give you the game plan or idea of this proof by looking at the trio I have over here. So you notice I have children for each one of my nodes. Which node does not have a child? Which one? This one? No, this one, actually, this one has no children, right? Okay, that one has children, that has no children. Which one has a parent? Okay, which one? This one has a parent, this one has a parent, that has a parent, that has a parent, that has a parent. This one does not have a parent. But remember, each one has a unique parent. So here's going to be what the counting argument we're going to use looks like. Let me get a different color here, because I find it more fun to do it this way. So each one of these nodes has a unique parent, right? That means that there's an edge connecting that node to its parent. So all I'm saying is match each one of these to the edge. So just like attach them almost like a sucker. Look at these as like a sucker. And you ask yourself, how many suckers are there? How many suckers are there? And try to relate that to the number of vertices or nodes in the tree. How many are there? So pair every node with the edge connecting it to its parent. Now, if I do this, which node is the only one that does not get paired with any edge? It's the root, right? One node, getting ahead of myself. One node will not be paired with the root. Therefore, how many edges are there then? Well, there's 1, 2, 3. So for example, my picture here, keep in mind, remember the picture is not a proof. So how many do I have here? If I have 1, 2, 3, I have 6 nodes. And how many edges do I have? 1, 2, 3, 4, 5. Right? I have 5. 1 less. Why? Because I can pair each one of the nodes with an edge connecting to its parent. The node is not counted. That means that there's 1 less edge than the number of vertices. Therefore, there is 1 less edge than nodes. Right? See, is that not that very hard to see? So there has to be one less edge than the number of nodes because the root does not have one I can match it with. This is a very simple argument where I'm just pairing and counting. Does everybody understand that? This is a very simple proof. I like this proof. So it's one less edge than nodes. How do you know? Just think of it like I have a bunch of suckers and I attach them together like this. Which one isn't? It's the root. How many vertices are there? N. How many edges are there? One less than the number of vertices. N minus 1. Okay? It's very nice. Now let's talk about how we can do things with a tree. Okay, so I'm going to first talk about one problem that I think is a nice one to illustrate the recursive nature of a tree. I'm going to talk about computing the height of a tree. Remember, the height is the maximum depth of the tree. Now, I'm going to draw out a tree first, and I'm going to we'll come up with a so-called recurrence relation that will basically spit out the algorithm for us. So I want you to think very carefully about this. So imagine I have the root r. I'm going to have 3 children off of the root. And from the rightmost one, I'm going to have 2 children. And from the rightmost of that child, of those children, then I'm going to have 2 children. On the leftmost child, I'm going to have 2 children. Okay, without being too meticulous here, what's the height of this tree? Okay, well, we look for the node with maximum depth, right? It is the maximum number of ancestors possible. You can think of it as the maximum number of edges from the furthest root away from, from the furthest leaf to the root. So how big can it be? Well, 1, 2, 3. So you notice that the height of this tree should be 3, right? Now I'm going to think about this in terms of subtrees. Now remember, if I pick a node, the subtree consists of the node and its descendants. So I want you to ask a very simple question. I'm going to pull out a different color marker because I think it will help a little bit. Before thinking about how you do it for the entire tree, think about what you do with a leaf. What's the height of a leaf node in a tree? So if I just give you a tree where it just consists of this node, what's its height? How many ancestors does it have? It has none, right? Its height is 0. So that means that all of these leaf nodes all have height 0. So all of these have 0 for their heights. They have no ancestors. Because remember, in terms of their little land where these leaves are all of a sudden the root nodes, they are the kings and queens of the tree. So they have no parents, means that they have no ancestors. They're the be-all, end-all. Okay, so now I know that the height of this subtree is 0, and that subtree is 0. What's the height of this tree? Well, it's the maximum depth of any node in the tree, right? But what are its children? Just these 2. So what's the height of this tree? It is 1. Okay, what's the height of the tree, the subtree here? If I consider this node, it means all of its descendants. Well, now that you know what the height of all of its children are, okay, so you know the height of this tree, and you know the height of that tree, the one I've outlined in blue. What's the height of this tree then? Well, clearly can't be any higher than either the maximum of 0 or 1 plus 1 ancestor, right? Or 1 edge. So the height of this tree must be 2. How about this one? Same idea. The height of this one is 1. The height of one is 0. So what's the height then? Well, the great thing is I've considered all the children already. Look at this. I just picked the largest of these 3, and I add 1 to it, right? Notice that I have one more ancestor possible. The way you got to look at it is, imagine I had the leaf with the maximum depth. What I'm doing by doing this is I always consider the maximum every single time I go up the tree from a leaf. And by doing it and considering all the possible subtrees, I can eventually reach the root. And what's the height of the tree? Well, it's the maximum of these plus 1, which is 3. That's it. It's really that simple. So let me write down how we can compute the height in a bit more of a mathematical way, and then I'll write it down in pseudocode. Because once you write it down as a recurrence relation, you can see very quickly that you can write it as in this way. So the height of R is equal to the following. So imagine that R is any root of a tree. So it's 0 if R is a leaf, right? That's what we established. Or it's the other possibility. It's the max among the children of R. Or I take the height of the child. So I'll give the name of each child. I'll call this child C of R. So I consider all the children of R, and I compute the height of it, and I take the largest of these, and I add 1 to it. So that's if R is internal. And those are the only 2 possibilities, right? So if I give you any node in this tree, I can compute the height recursively by doing this. So here's the algorithm. Let me write it over here. So the algorithm is, I'm going to call it height. Height R is input is root R of the tree. And the output is the height of the tree. So we're going to first have if R is a leaf. So if R is a leaf, then what are we going to do? Well, according to our recurrence relation, I should return 0. So I return 0. This is actually our base case. So we're going to have a base case and a recursive case. This is our base case. Else, we're going to have a variable that's going to keep track of the maximum height we've encountered so far among the children. I'm going to start off and set it at -1 because it's either going to have no children or more, right? It can't have negative children. So I'm going to go for each. So I'm going to use a for each child C of R. So I'm going to do this for each one of the children of R. This is where children, the method I referred to earlier, becomes relevant. So I compute the height of the child. I'll call it H. So H is going to store the height of the child. And so remember, all I'm going to do is I'm just going to keep track of the maximum height I encounter. So if H is greater than max height, then I'm just going to update max height. I'm just going to reassign max height to be the value of H. And that's it. And I'm just going to return max height plus 1. That's it. And there you go, that's the height. It's not too terribly complicated. Remember, if I know I have a leaf, its height is 0. Otherwise, I have to consider the maximum height among my children, which we can apply recursively because I can recursively break the tree apart and think about it in terms of this top-down approach where I keep recursively going down and considering each subtree and computing its height. Okay? So now I'm going to do the analysis. Okay. What did we do in the past? What I did was I normally ignore the recursion and treat it like a single step. And then what I did was I counted up all the operations that are done. And then I count up how, so I do all the non-recursive work and then I figure out what's going on with the recursion, right? That's normally what I do. So I'm going to do something quite similar to that here. First, let us analyze the algorithm, ignoring the recursive calls. So the first line right here, it takes some constant number of time, right? The first line takes some C1 operations the lines inside the else block but outside the loop take some C2 operations. So I'm talking about the lines that are occurring outside the else block, but not inside this loop. Then C3 operations inside the loop. How many times does this loop iterate? The number of children of R, right? The number of iterations for the for loop is the number of children of R. So how long does this loop take? Well, it's some constant times the number of iterations of this. But how many iterations are there? The number of children. So the loop takes C3 times numchild of R. Remember, numchild is the function we gave, or method we gave, that tells you how many children there are. So this is our main observations. I've just laid out all the constants. Now let's actually compute the time complexity. Okay. There are C1 operations in the base case. And C2 plus C3 times numchild of R operations in the recursive case. I want you to notice that I don't call my recursion on a child twice, right? I only do it once per node. So observe that the number of calls is 1 per node. Thus, time complexity or total number of operations is, so I'm going to use some summations again. So the sum of all the C1s, now these are over all the leaves. So all I'm doing is I'm considering all the cases where I encounter a leaf in my tree. How much time occurs or how many operations occur in the base case? C1. How many times does that happen? It happens for each one of the leaves. So I would just count up for each of the leaves in the tree, that many times C1, plus for the internal nodes of the tree. So I'll have internal, so I'm going to sum over all the internal nodes. So imagine I have each of the internal nodes of the tree. So I'm going to give it a name, I'll call it U. For each one of those, I'm going to do C2 plus C3 times num_child. Now note that's a multiplication there, not an X. I'll just put a dot here, just to be a little bit easier to see. Num_child of U. So what is this if I simplify that? Well, it's equal to C1 times the number of leaves. So I'm just going to keep things somewhat informal. So C1 times the number of leaves plus C2. How many times does this happen? For C2, I'm going to split apart this summation. So I'm going to write the sum of all the internal nodes with C2 plus the sum of all C3 times the num_child. So I'm going to split this apart. So how many times does this occur? The number of internal nodes, right? Times the number of internal nodes. So number of internal. So I'll use number of internal, number of leaves to be simplifications of number of internal nodes and number of leaves. And then lastly I have C3. Because C3 gets multiplied to each one of them, I'm just going to pull that out. I'm just saving myself a little bit of a step here by doing this. So for each one of the internal nodes, I sum over num_child of U. So I want you to think about this. So these reports seem okay. We know that that's going to be at most n, where n is the number of nodes. This is also at most n. What is this? What's this? What's that? The number of internal nodes. Well, the sum of the number of children over number of children, let's just say over, let's go for all the internal nodes is the number of edges. Edges M. And remember, I had a theorem, right? We were just going to invoke that theorem right now. So M is equal to n minus 1. So the number of operations, or ops, is equal to C1 times the number of leaves plus C2 times the number of internal nodes, right? Internal plus C3 times n minus 1. Well, what's this in terms of big O? This is big O of n. And we're done. So this is a linear time algorithm for the tree. So the reason why we call it linear is because the input size for our problem is the tree itself, which is consisted of the number of nodes it has. So the number of nodes is n. So we say this is a linear time algorithm. Okay. So we're going to talk about tree traversals next. How you can navigate through a tree. Now you may have seen some tree traversals in the past. I'm going to give somewhat more general versions of these if you've seen them before. What's a tree traversal? A tree traversal visits the nodes of a tree in a systematic manner. So there's two main kinds I'm going to talk about here are pre-order and post-order. You may have heard of these before. Pre-order traversal. And then we have, so pre-order traversal, just I'll write it out now. So the rule in the pre-order traversal is that a node is visited before its descendants. So hence the pre in pre-order traversal. So it's going to visit them before the descendants. In contrast, a post-order traversal, you might guess based on the prefix of order, a node is visited after its descendants. Okay, so I'm going to quickly write out the algorithms for these. Now keep in mind these are high-level descriptions of them. So I'll just write them down here because they're really simple. I'll write both of them. So each of these is going to be given some node. In the pre-order, it's going to visit V. I don't know what visit exactly does, but it's just some operation. Then what you do is for each child, C of V, do the following. So for each one of the children, you're going to apply pre-order of V. You might actually guess what's going to happen here. I'm just going to write the loop first for each child C of V. Do, and you'll do post order. Capitalize the order in order. Post order C. And that also should be a C. Because remember, we want to apply to the children, not the node itself again. And then after the loop, I just visit V. So pre-post, pretty straightforward, right? What you do is you traverse the tree by considering either itself before its descendants or after its descendants. So this is the general framework for these two algorithms. So one, in the pre-order, you visit each one of your children after you've visited yourself, or you do it after, okay? I'm going to show you an application of the post-order traversal. This might be the last thing I'll show you today. So here's an application of post order. So what we're going to do is I'm going to consider computing the space, used by the files in a directory and its subdirectories. So let me draw you a picture. So imagine I have my highest most directory being Seaside 255. And it has in its directory, let's say 2 folders and a file. The file is going to be called todo.txt. Maybe this is some of your homework or like a to-do list you have for the class. We're going to say that this is 1 kilo of memory. I'm not going to worry too much about the measurements here. It's 1 kilo. Maybe we can kilobytes. I don't know. Then we're going to have a folder for programs. Now, for each one of these directories I have here, what I'm going to each one of them is going to have some space associated with them. So 1K for each one of these. This is going to be my assignments folder. And so in the programs folder, I'm going to have maybe some Java files. So I'm going to have ddr.java. Now, maybe you felt like playing Dance Dance Revolution or something. Maybe in your spare time when you're not playing Dance Dance Revolution or you're trying to write up your own Dance Dance Revolution type of solver. You like to look at the stocks. So I have stock or stocks.java. And maybe after, when you're hot whiz, after you work on your DDR, while you're calculating up stocks, you work on robots. Maybe you want to model out a robot. I'll call it robot.java. It's 20K. Over here, I have maybe my assignments. Maybe I have some document file. Maybe done in Word or something. And then I have a1c.doc, which is going to be 2 kilos. Okay, so I've laid out all the files and the directories. And my question is what the total space is. So what I need to do is I need to compute the total amount of space used across all the directories and files. So I need to add up all of these. I need to add up the sizes associated with these and that file. How much is it? If you were to add them all up, the total space being used here is 64K. Now you might naturally ask, oh, well, Dan, how exactly, why would we care about this? Well, there's all sorts of processes on trees that are going to resemble a structure that looks like this. Or I have some tree, I need to explore something, but I need to compute something about the tree. such that I go through all the elements and I am able to sufficiently add them up in a very nice and simple and elegant way. So what's one way you can compute the total space? So what you can do is you can consider all your children and then you count up their space. So if I get here and I want to compute the space, what I do is I consider its children, count up the total amount of space they use. I can do the same thing recursively all the way down. But when I'm done doing that, what I do is I compute the space used by all the things that are my children plus my space that I use to occupy. So whether it be a file or a directory. So this is naturally something you could write down as a post-order traversal. So let me write out an algorithm for you that captures this idea. So here's the algorithm. I'm going to call it this space. And it's given R. Input is as follows. It is the root R, so it's the root node, root R of a file system tree. So remember I told you that file systems can be trees, and this is exactly what I mean by this. So you see my tree layout here? I'm going to use the fact it's a tree to compute the disk space. So the output is going to be the total space used by the file system. So remember, the big idea here is that I don't know what the total space used of this subtree is until I consider all of its children and in particular its descendants. So the idea is I do all of the space used of my descendants, then I add it to my space. Okay? So that's the idea. So I'm going to have a variable s. It's going to be 0. It's going to be the amount of space that my children are going to use. So first I consider all my children for each child C of R. Do the following. We're going to assign S to be the disk space. So I'm going to give it disk space recursively. I'm going to apply it on C plus S. So all I'm going to do is I'm going to count up the disk space used by each one of my children. Then after I'm done this loop, I'm going to return S plus my current space, R dot space. I'm going to assume that there's just this ability for me to access as an attribute the space. I'll call it space like this. This is one of those modeling things about the tree. The files have space. They occupy their size. So this is just the algorithm. It's very simple. So what we're going to do is I'm going to quickly try to talk a little bit about the time complexity. And maybe when we come back, we'll talk about the space complexity. You're going to find the analysis here is going to be very similar to the one we did before. So first we ignore the recursive calls. The first and last line take, how long do they take? The first and the last one, this and that. Assuming the space is going to be computed in constant time, it's going to take some constant operations. It takes C1 operations. And the line inside the for loop, takes C2 operations. And how many iterations are there of this loop? It goes through each of the children, right? And the number, this isn't really a proper sentence, but we're going to go with it anyways. And the number of iterations of the loop is what? It's numchild, right? Numchild of R. So what's the total number of operations? So I'm going to say the total number of operations ignoring the recursion is C1 plus C2 times numchild of R. So how many were made for the recursive calls? Well, it's one per node, right? It's the same thing we did before. Because remember, I applied to each one of the children. I don't apply to a child twice. So it's once per node. So there's the root itself, and then it's all of its children, but that's each node in the tree, right? So, let me rephrase this. I'll say, notice that the number of recursive calls is one per node. So naturally you'd want to justify this. We're not going to for the sake of our explanation. One per node. I think everybody can be convinced by this fact. So the time complexity now let me write it as a function because it makes it a little easier to play around with. So f of n is going to be, for each one of my nodes in the tree, I have C1 plus C2 times numchild of u. What's this equal to? Well, I can split this summation up. So I sum over all the nodes in the tree. So I have C1 plus, each one of these is multiplied by C2, so I'm just going to put that C2 in front of the summation, because it's just redundant to put it inside. For each one of the nodes here, numchild of u. Oh, we already know what this is, right? What is that? Therefore, the time complexity is C1 times n plus what? How many children are there? How many children are there for each one of the nodes? If I sum across all the nodes, do the leaves have any children? No, right? So that means we're talking about the number of edges again. What's the number of edges? It's the number of vertices or nodes minus 1. This is big O of n. And we're done. Lickety split. So we've used this lovely property of trees to come up with the time complexity here. So next day we'll come back and we'll compute the space complexity of this algorithm. And then we'll start talking about some more interesting things involving trees. So thank you very much, and have yourself a beautiful day.